Hi class, let's do some linear algebra. Today we're going to be talking about diagonal versus diagonalizable matrices. Definition. A diagonal matrix is a matrix where the only non-zero entries of the matrix are along the main diagonal. Said otherwise, in notation, say A is the matrix Aij. Aij is going to be 0 whenever I is not equal to j. Let's remind ourselves of a little example. Example, here is a diagonal matrix because the non-zero entries are along the main diagonal. And here's a non-example, 0, 1, 0, 3. This is not diagonal because this entry is non-zero, but not along the main diagonal. So this is diagonal, and this is not diagonal. All right. As we've explored before, the reason that we like diagonal matrices is for two main reasons. Well, lots of reasons really, but for two main reasons. That it's easy to find powers, and it's easy to find inverses. We've spoken about this in another video. The problem that we have is that not all matrices are diagonal. However, there are matrices that are close to diagonal in the following sense. There are matrices that are diagonalizable. Definition. A diagonalizable matrix is a matrix that is similar to a diagonal matrix. Said otherwise, there exists a non-singular X and a diagonal matrix D such that X inverse A, X is equal to D. This would mean that A is diagonalizable. Let's do an example. 1, 1, -2, 4. If we have 2, -1, -1 on one side, and 1, 1, 1, 2 on the other side, we get 2, 0, 0, 3. Where this matrix is A, here we've got X and X inverse, and this is our diagonal matrix D. Let's do a non-example. A non-example. 1, 1, 0, 1. It's not diagonalizable because it does not have linearly independent eigenvectors. We've explored this in another video. So for a diagonalizable matrix, we have X inverse AX is equal to D, or A equal to X DX inverse. So for example, for the matrix that we had before, this would be 1, 1, -2, 4 is equal to 1, 1, 1, 2, 2, 0, 0, 3, and 2, -1, -1, 1. Okay, this video is about diagonalizable matrices and how they compare to diagonal matrices. So let's talk about finding powers. If I had a diagonal matrix and I wanted to take it to the power n, this would be the same thing as taking the individual non-zero elements of the diagonal matrix and raising each of those to the power n. Let's see what happens with diagonalizable matrices. Let's do the theory, and then let's do the practice. So let's look at A is equal to X dx inverse. A squared is therefore going to be X dx inverse times X dx inverse. And because matrix multiplication is associative, we can actually reassociate, and this would be identity. What we get is X d dx inverse, which is X d squared x inverse. Let's look at A cubed. This is going to be A squared times A, which is xd squared x inverse times xd x inverse. Since matrix multiplication is associative, this is I, and what we actually get is xd squared dx inverse, which is xd cubed x inverse. I'm sure you're seeing a pattern now. For a diagonalizable matrix A, such that A is equal to xd x inverse, what we have is that A to the n is going to be equal to xd to the n x inverse. And one thing before we do an example, this means that we have the following fact. Powers of diagonalizable matrices are also diagonalizable using the same matrix X. All right, let's do an example. Remember that A is equal to 1, 1, negative 2, 4 as above. We want to find, or at least figure out how to find easily, the 15th power of this matrix. So A, if you recall, is 1, 1, 1, 2, 2, 0, 0, 3, 2, negative 1, negative 1, 2. And so A to the n is going to be 1, 1, 1, 2, 2, 0, 0, 3 to the n, 2, negative 1, negative 1, 1. So in particular, A to the 15th is going to be 1, 1, 1, 2, 2, 0, 0, 3 to the 15th, 2, negative 1, negative 1, 1, which is 1, 1, 1, 2, 2 to the 15th, 0, 3 to the 15th, 2, negative 1, negative 1, 1. So now we have a way to easily express the powers of diagonalizable matrices. Another thing that we've highlighted about diagonal matrices is that their inverses are easy to find. Let's talk about inverses of diagonalizable matrices. So remember, for your diagonal matrices, say we've got 2, 0, 0, 3 as usual, and I want to find the inverse of that. It's going to be 2 inverse 0, 0, 3 inverse, which is a half, 0, 0, 1/3. Let's talk about what this means for diagonalizable matrices. So say, as usual, A is xd x inverse. All right? Here's what I want you to notice. What's A times xd inverse x inverse? Well, this is xd x inverse times xd inverse x inverse. Matrix multiplication is associative, so here we've got I, and what we get is xd d inverse x inverse. D inverse is again I. We get x inverse, which is I. Similarly, xd inverse x inverse times A is also going to be I. Putting that all together, what do we get? For diagonalizable matrix A such that A is equal to xd x inverse, A inverse is xd inverse x inverse. From this, we can see the fact. Inverses of diagonalizable matrices are also diagonalizable using the same matrix X. Let's do an example. Here's our running example. A is 1, 1, negative 2, 4. We want to find the inverse. We know that A is equal to 1, 1, 1, 2, 2, 0, 0, 3, 2, negative 1, negative 1, 1. So A inverse should be 1, 1, 1, 2, 2, 0, 0, 3, inverse 2, negative 1, negative 1, 1, which of course we know is 1, 1, 1, 2, 2 inverse, 0, 0, 3 inverse, 2, negative 1, negative 1, 1, and here is our final expression. Okay, what have we learnt? That while not all matrices are as awesome as diagonal matrices, diagonalizable matrices have very similar properties, and we can extend what we know about diagonal matrices to diagonalizable matrices in order to find the inverses and the powers of diagonalizable matrices. Now, what is all this good for? Well, it turns out that diagonalizable matrices and their powers are essential in analyzing Markov processes. More on this later.